chapter is all about derivatives. And derivatives, we've already kind of learned what a derivative is. And it is a derivative is the instantaneous, that's not very good, and instantaneous rate of change. Rate of change of a function and that's what a derivative is. Okay? Now you will see the derivative in several different forms. Okay? Sometimes they write it like this. This is the way I most frequently write it, f prime of x. That means the derivative of a function. You will also see this notation, just sometimes you'll see like y prime. These all mean exactly the same thing. Sometimes you'll see f prime. Sometimes you'll see dy dx. That means change in y. It's instantaneous rate of change y with respect to x. Sometimes you will see, and I haven't seen this one very much, but apparently they do use this one in the book quite a bit, df dx. That means the rate of change of the function with respect to x. And you also see this notation, where is it? ddx of f of x. So this one's kind of the longest one, right? It means the derivative with respect to x of some function f of x. This means the same thing. This just means the derivative. They all mean the same thing, but it's different notation. And sometimes we'll be going fast and you'll say, what's the difference? There is not really any difference. This one, you'll see when we do some differential equations and stuff like that. Okay? So the instantaneous rate of change of a function. Anyone know why you would want to know the instantaneous rate of change of a function? Very good. So you can find the speed of an object at any point. As a matter of fact, I guess I was reading the good old history in the 17th century, this calculus was kind of developed, and it was very important for properties of how orbits work and planets and all that. They could finally figure out this planet is so far away because they're looking at how fast, it moves from here to here, and how is that changing from here to here. And that's how they figure out, this planet sun is 93 million miles away or something like that. I think that's how they do. I'm not an astrophysicist, but apparently they use calculus a lot for describing motions of planets. And businesses too. Why in business would you want to find out the rate of change of something? Yeah, you want to see now my profits are increasing, maybe now they're not increasing as fast. How could I change that? Population growth, population's growing really fast, and then it starts leveling off. Why? How could I adjust for that? Do I want to adjust for that? All kinds of things. So there are lots and lots of applications, not just in math, but in all different walks of life where you would be concerned with rates of change. And that they do use calculus for. Now, unfortunately, for most of the rest of the chapter, we're not going to see too many applications until later on. We're just going to kind of do some calculus. And there's a lot, this chapter is a little more like plug and chug. This is how you do it, now do it, and it's not quite as theoretical as the limit. So that's why I think it gets a little bit easier. Okay? So the definition of a derivative, so let me write in a different color. Okay? Definition, and I just wrote that on the board a few minutes ago. So if you feel tired of writing this down over and over again, derivative of a function, okay, is f prime of x. Instead of calling it the slope of the tangent line, which we've been calling it, the f prime of x is equal to the limit of that function as h goes to 0 of f of x plus h minus f of x over h. And this is to find the general equation of a derivative. Okay? So let's do one that, provided it's differentiable. Provided that the function is differentiable. differentiable. Ooh, that's a good one for Scrabble, right? Differentiable means you can take the derivative there. Okay? So functions that are differentiable differentiable on an interval are usually ones that are smooth curves and things like that. Things that are not differentiable are things like would have sharp points in them. And the reason they're not differentiable because it's differentiable everywhere except at this sharp point C, because like coming in here the slope is very what? Is it positive or negative? Positive, and then it turns immediately and it goes negative. So if a function has that's called a cusp, like a sharp point, or if it has a hole at a point, like here, okay? Or if it has a jump discontinuity, like here, we'll talk more about differentiability, then it's not differentiable. Or an asymptote, and it's not differentiable. So it's got to be smooth at that point. It's got to hook up nicely. Can't be having any jumps in it or anything. Okay? So let's do one that we haven't done before. Okay? Go away. Okay? So let's find the derivative of, find the equation of the derivative of y equals x cubed. Okay, so we haven't done a cube one yet. I think we might have, but just kind of in passing. So this is kind of using the same, using the definition. So we're going to use the definition not by using the shortcut rule, which many of you know already, right? Don't you know the shortcut? Well, I'm not going to tell you the shortcut rule yet. Okay? So using the definition of derivative, we're going to do this. So what I'm going to do is f prime of x is equal to x plus h cubed, right? That's f of x plus h minus f of x, minus f of x, which is just what? X cubed over h. Whoops, I forgot something. I want to take the limit of that, limit as h goes to 0. So f prime of x is equal to this. So in this case, since I taught pre-calc for a number of years, I remember the binomial expansion. If you don't remember that, you would have to multiply x plus h times x plus h times x plus h. Or you could remember that the coefficients of this are the coefficients in Pascal's triangle in the fourth row down. Okay? 1, 3, 3, 1. And it starts off with an x cubed plus, then the x cubed goes down to an x squared, h, plus, then the x squared goes down to an x, and the h goes up to an h squared, plus 1h cubed minus x cubed over h. Okay? So I'm going to take the limit of this as h goes to 0. All right? And what happens with those x cubes? There you go away. And very nicely, things disappear very nicely when you do this. Those x cubes go away. And also, what else can, now that the x cubes are gone, I'm going to take cheat with a couple steps. What else could I cancel out? You see how there's 1h over here, so that turns into a 1. There's an h squared over here, that turns into an h. There's an h cubed over here, that turns into an h squared. And this just turns into a 1, right? See what I did? I pulled out an h out of all those terms. After I should have taken 2 steps. But this minus this disappears, which allows me to cancel out an h out of the top and bottom. So now I have the limit as h goes to 0 of 3x squared plus 3xh plus h squared. You guys have any questions on the algebra there? You kind of get that? Algebra, I'm going to kind of go fast, and then you guys could go back and say, what did he do there? You know, and you'll figure it out. Okay? And then I just take this 0, and I plug it in for h. And what happens to this term and this term? Goes bye-bye, right? And I get this is equal to 3x squared. And so this is f prime of x, which is just what Will said because he knows the shortcut, right? Okay? So you should be able to do that. And this is good practice for your test because I asked you to do the limit process except with a point instead of with a. You're not going to have to find the equation, but anyway. So now this y equals x cubed, it kind of looks like this, which you know, right? You know that. And so say, for instance, I want to find the slope at 2. What's the slope of the tangent line at 2? Very good. It would be 12. I would take 2, and I would plug it in here, guys, and then I get equals 3 times 2 squared, which is 12. So as you can see, probably it kind of looks right, because at 2, this curve is very steep, right? I probably didn't draw it to scale. But it's very steep right there, so it would have a steep slope. If I want to find the slope at 0, what would be the slope at 0? 0. So actually, I probably drew my curve kind of wrong. It's probably going more like this or something like that. That would, okay? You get that? So with the equation of the derivative, you could find the slope at any point on the function, which is really kind of cool. All right? All right. I have 10 more minutes. Maybe I'll finish. I'm doing good. Doing well, sorry. Okay, so then we have the derivative of a point, derivative of a function at some point A. A, okay? It would be A comma f of A, actually. So the definition of that is f prime of A, which is how we would write it, is equal to the limit, and we already gave you this one as well, as x, oh, we haven't given you this one. This one's a little bit different. As x goes to A of f of x minus f of A over x minus A. So this is a little bit different from what I've seen before. So say, I don't know, I have some function which goes down, and it looks like this. So here is the point A. Here is x. We'll call this x. So x is a variable, okay? And what I want to do is find the slope of the tangent line exactly at A. So as x approaches A, do you understand that I approach the slope of the tangent line? Okay, because this is f of x, this is the y, f of A is the y, x minus A is what we call the h before. But sometimes this definition is better when you have funky looking functions, okay? I mean, you could use the other one, but this one will work for functions like this. For example, find the derivative for f of x equals root of x at A. Okay? So this is how you do it. You would take the limits as x goes to A, And if you try to, I kind of tried to do this one with the other definition, and you have to do some really tricky things if it works at all. Okay, so because the h's don't cancel out and stuff like this, so this is a little bit tricky. So what you do is you plug in f of x, which is just what it is right there, root of x. F of a is just root of a over x minus a. And what as x goes to a means, it means you take a and you plug it in there for x. Okay? What happens if I plug in a in here? I get 0 over 0, or I get something over 0, which is undefined. So I can't do that, so I have to do a math trick. So the math trick I'm going to do is I'm going to multiply the top and the bottom by the conjugate of the top, okay, which we haven't, usually we used to rationalize the denominator, but now we're rationalizing the numerator. Do you remember doing this? Multiplying by x plus a. And what happens here is you get that this is equal to the limit, and you got it, this is why you got to like practice these, because I messed up before. What's root of x times root of x? X. What's minus root of ax and plus root of ax? They disappear, right? See, this term, the inner term and the outer term disappear, and then I get minus root of a times plus root of a, which is just what? Hello? Minus a. And on the bottom, this is where you got to be careful. You don't want to multiply this together. You want to leave this as x minus a times root of x plus root of a. Okay? And the reason that I do that is because what happens, what can I do with these now? I can cancel out this, and I get that this is equal to the limit as x goes to a of 1, there's a 1 there, right, when I cancel, over root of x plus root of a. And now I can plug in a in here, and I get that's equal to 1 over root of a plus root of a, which is the same as writing 1 over 2 root of a. Okay? So why would that be useful? Does anyone know what square root of x looks like? Y equals square root of x looks like?
It's like half of sideways.
Yeah, it's like half of a. It's like this, right? So if I want to find the slope of the line at 3, for instance, it would be 1 over 2 root of 3, which is 1 over 3.4, which is, I don't know what that is, it's like 0.3 or something. So it looks like it has a pretty shallow slope there, right? Okay? Follow that? Kind of tricky, I know. Okay? And then last thing I want to talk about, and I guess I will have a little bit of time to talk about this, is they also talk about left and right-sided derivatives, which I think you can figure that out. Okay, left and right-sided derivative. It's just a slope coming from the left and the right. But a nice thing to talk about, which always comes up over and over again on AP tests, is something like this. I'm going to draw this one. And over here I'm going to put a 1. Don't go away yet. This is important. Over here I'm going to put a 2. Over here I'm going to put a 3. And I made this one up. And over here I'm going to put a 4, even though it's not to scale. And over here I'm going to put a 5. And then I'm going to kind of say that it goes like this. And this is f of x. And they're going to say sketch f prime of x. Okay? So these are fun. These are like thinking problems. Watch. Real quick. Don't go yet. Please don't go. Don't go yet. 1, 2, 3, 4, 5. Think about it. 1, 2, 3, 4, 5. Okay. What is the slope here? Negative or positive? From here until I get to here, the slope is negative, and then it's what at this point? No, at this point it's 0, right? So you have to think you're looking at a picture of the slope, okay? So it's going to start off, maybe it's -1 or something. I don't know exactly what it is, and then the slope is 0 at 1. At 2, the slope is negative or positive? Positive, but then at 2 it's positive, okay? And it's going upwards, something like this. But then right here, it starts, the slope is still positive, but it starts getting less positive. And back at 3, the slope again is 0. See that? Okay? Then the slope is what? Negative until I get to where?
Like 4.5.
Well, let's say that I made this to go through 5. Wait, at 4, at 3 the slope is 0. Then up to and going through 4, the slope is still negative, right? And then at 5, the slope is 0 again. So if this is f of x, this would be f prime x. So that's a lot of thinking, right? Yeah, and then they actually go backwards. Here's a derivative, sketch the function. Okay, so those ones are really, you can look at the one in your book like that. Your homework is on my website on chapter 3. I don't believe it's that much, so you'll be okay. Thanks. If you have questions about your quiz real quick, come
Wait, can you put the review like so